In this video, I'll be looking at how you quantify uncertainties in measurements, how we make an estimate for that value, and then how we carry those forward when we do calculations with those measurements that have got uncertainty. So we're looking at the rules for how you carry them forward. In a subsequent video, I'll go through some exam questions so that we can see how you use these rules in practice. So let's start off by thinking about absolute uncertainties. The absolute uncertainty you need to get from the smallest scale division of the device that you're measuring with. So that's called the absolute uncertainty. And the way that you would write your measurement with the uncertainty is to write your measurement value, then plus or minus the uncertainty, followed by the unit. And these two numbers here must have the same number of decimal places. So where this one ends, this one actually controls where you would write the number of decimal places in the measurement. So where that one ends, that the measurement must end as well. So take the most obvious example, a meter rule. If you look up close at the meter rule, then the smallest scale division on there is 1 millimeter. So that's going to be my uncertainty. If I measure this blue rectangle here, then this would be 54 plus or minus 1 millimeter. It's 54 millimeters long according to the ruler, and the smallest scale division is 1 millimeter. So I've got my measurement, uncertainty, and then the unit there. That's not the only way that you could write that, but we'll look at some more examples in this slide here. So whenever you take the measurement, you write to the first significant figure of the uncertainty, so they have the same number of decimal places. And if I look at my previous example written with 3 different units, first up, I started off by stating the measurement was 54 plus or minus 1 millimeter. But you don't have to state it in millimeters, you could state it in centimeters. So 54 in centimeters is 5.4. So I could state it as 5.4. Then 1 millimeter in centimeters is 0.1. So that's 5.4 plus or minus 0.1 centimeters. And then again, if I wanted to write it in meters, then I could write it as 0.054 plus or minus 0.001 meters. Hopefully you get the idea now. That's how you could write your measurement with the absolute uncertainty in various units. If you're putting data into the table, then you indicate the absolute uncertainty or the precision of your measurements by the number of decimal places that you include down the column. So all of these values are measured to the nearest 0.001 of a meter. So the uncertainty there is plus or minus 0.001 meter. Same precision as these, because that's a height. It's measured with the meter rule. And then I've got these time values over here. And these, I'm indicating the uncertainty as plus or minus 0.01 seconds there. They've all got 2 decimal places, okay? So these are all measured with the same measuring device, so they should have the same level of precision, the same uncertainty. And these have different to the time values, but they're all consistent with each other. The heights are consistent, the times are consistent. Now let's look at percentage uncertainties. What we've seen so far are the absolute uncertainties. The percentage uncertainty, to calculate that for a measurement, you take the uncertainty, the absolute uncertainty that is, you divide it by the measurement, multiply it by 100, and that's your percentage uncertainty. So let's take some distance measurement as 0.650 meters. That's measured with the meter rule. So from that I can ascertain that the absolute uncertainty is plus or minus 0.001 meters. The percentage uncertainty for D, which I'm going to write, all my percentage uncertainties I'll write as the percent then the variable, would be 0.001 divided by 0.650 multiplied by 100. That gives me 0.154%. If I wanted to do that with a time measurement, where the time is 0.97 seconds, I measured with it with a digital stopwatch, so that's measured to the nearest hundredth of a second. The percentage uncertainty in T then would be 1%, according to that calculation there. Okay. Now you're going to see the usefulness of percentage uncertainties when we come to do seeing how the uncertainty affects calculated values. But before we do that, we're going to need to know how you convert a percentage uncertainty into an absolute uncertainty. If you're given a percentage uncertainty, you need to work out the absolute, then you multiply the percentage uncertainty by the measurement. So let's look at some examples of that. If my percentage uncertainty in D is 0.154% and D is 0.650, then I multiply those two. Because it's a percentage, I need to divide that by 100. You can use the percentage button on your calculator as well if you want, or just appreciate that it's 0.00154. Multiply it by 0.65, and I get my uncertainty as 0.001 meters. And then you can do the same thing with T as well. T is 1%, and when I multiply 1% by 0.97, I get 0.01 seconds. So that's absolute uncertainties, percentage uncertainties, and how you convert a percentage to an absolute. What if you have repeated values, such as in a table? The uncertainty of repeated values is half of the range. So here's a table. This is the same table I had before, but I've got my average values here now. And that average is based on these repeats here for the times. So let's look at the top one here. The range between these two is the largest value might take away the smallest, so that's 0.01. That's my range. So my uncertainty is half of that, which is 0.005. And this has a larger range of 0.03, so the uncertainty is now 0.015. And for these values here, it's 0.02, so it's plus or minus 0.01. You might see different ways of calculating the uncertainty of ranges. Sometimes some people would say it's the range. Sometimes you'll see it stated as half range. Well, our example would use its half range, so that's what I'm stating here. So let's do the percentage uncertainty for the average value of row 2, which is this row here. I've got my uncertainty here. That's the value of the measurement that I'll be using. So the percentage uncertainty of the average value of 0.7 is 0.015, so that's my absolute uncertainty, divided by the measurement, multiplied by 100, so that's 2.1% for that value. And then you could do the same procedure for the other rows as well. This principle applies, if you've got values in a table, but also if you were reading a meter, like a voltmeter or an ammeter, and you see that the value is fluctuating, you can take the highest and the lowest value, work out the range, and the uncertainty you could determine from half the range. Now let's look at what you do if you do calculations with measurements that have got uncertainty. Uncertainties in measurements will affect your calculated values, and there are 3 rules that you need to know for estimating the uncertainty in your calculated values. Rule 1 is if you are adding or subtracting. And I should say for adding or subtracting, you're going to be using values of the same type there. So you'd be using 2 lengths, 2 temperatures, 2 diameters, for example. So they will be measurements of the same type. You wouldn't subtract a diameter from a temperature, for example. Rule 2 is when you're multiplying or dividing. So this rule is very, very common because there's lots of multiplying and dividing. And rule 3, which is actually an extension of rule 2, and I'll show you how it's just an extension of it. This is if you have numbers that are raised to a power. So if you've got d squared, or a temperature squared, a time period squared, or something cubed, a radius cubed, any powers, rule 3 is the rule you use. So let's go at each one of those in turn. Uncertainty rule 1 if you have a series of measurements you're adding or subtracting, then you need to add the absolute uncertainties. So this one is very straightforward. Example uses, if you're calculating a temperature difference, if you're adding forces that you've measured with a Newton meter, or if you are calculating a height difference, then you'll need to use rule 1. Let's take an example. D1 is 10.0 plus or minus 0.1 centimetres, and D2 is 8.5 plus or minus 0.5 centimetres. So X then is calculated from D1 and D2. It's D1 minus D2. Notice that the rule says if I'm adding or subtracting, I add the absolute uncertainties. Now we're going to start off by calculating X. X is D1 minus D2, so this is nice and easy. 10 minus 8.5 gives me 1.5 centimetres. That's the value of X that I'm going to state. The uncertainty of X is the sum of the absolute uncertainties. So that's plus, it's 0.1 plus 0.5 centimetres. So that's 0.6 centimetres. That's my absolute uncertainty for X. So now I can state X as 1.5, that's the value I calculated, plus or minus 0.6 centimetres. And that means that the value of X lies somewhere between 0.9 and 2.1 centimetres. Note that both of my measurements had the same unit, they're both centimetres. If one was centimetres and the other one was millimetres, then I'd have to do a conversion for one of them so that they've got consistent units, and then I can A, do the calculation, and B, do the calculation for the absolute uncertainties. So yeah, watch out for that. Right, that's rule 1. Rule 2, which as I said is the most common of the rules to use. If you're multiplying or dividing, then you add percentage uncertainty. When would you use this? If you're doing a velocity calculation, distance over time, gravitational potential energy calculation, so that's mass times the gravitational field strength multiplied by the change in height, or a resistivity calculation, if you're calculating resistivity, RL over A. Did I say that right? RA over L, I do apologise. So whenever you're doing any of those calculations, then you're going to need to use this rule. So now let's look at an example for this. I've got a distance which is measured at 12.4 plus or minus 0.1 metres, and t is measured at 0.57 plus or minus 0.01 seconds. Velocity, the speed is distance over time. So let's calculate the velocity, or speed, sorry. I keep saying velocity. I'm calculating speed. So it's 12.4 divided by 0.57 gives me 21.8 metres per second. And now we've looked at the calculation of percentage uncertainties already. So I've calculated the percentage uncertainty for D as 0.1 divided by 12.4 multiplied by 100 gives me 0.8065%. I'm leaving all my values here to 4SF until the end, where I will then reduce the SF to whatever I need. The percentage uncertainty for T is 0.01 divided by 0.57 multiplied by 100 gives me 1.754%. So I've just stated those values there, but that's how you calculate them. Now I need to work out the percentage uncertainty in the speed. That is, following the rule, I add the percentage uncertainties. So it's percentage uncertainty in D plus percentage uncertainty in T. That gives me 2.561%. Now from that, if you're asked to just calculate the percentage uncertainty, you just leave it there. You've done what you were required to do. However, if you need to know the absolute uncertainty, then you take the percentage uncertainty, multiply it by the value that you calculated, that's 21.8, and that gives me plus or minus 0.5582 metres per second. That's for the absolute uncertainty of V. So now I can state that the value of V is 21.8 plus or minus 0.6 metres per second. And you notice I've rounded up to 1 decimal place there, or 1 SF. And I will explain that in a moment. The values the value for V then lies somewhere between 21.2 and 22.4, which is 21.8 minus 0.6 and plus 0.6. I've carried forward the one significant figure that I've stated here from the raw uncertainties. Both of these are 1 SF, so I've carried forward the SF in the uncertainties. Now, I haven't actually come across any uncertainties that are not 1 SF, so it's probably always going to be 1 SF. And notice the consistent numbers of decimal places in the measurement and the uncertainty. So that's how we do a calculation for rule 2. On to rule 3, the final rule. If you're raising a measurement to a power, then you need to multiply the percentage uncertainty of that measurement by the power. So, for example, if y is equal to a multiplied by x to the power of n, a is a constant, so it might be pi or just a straightforward 2 or 4, something like that. Then the percentage uncertainty in y, and x is my measurement, the percentage uncertainty in y is n, which is the power there, multiplied by the percentage uncertainty in x. Hopefully an example will clarify that. Where would you use this? Cross-sectional area of a wire, you'd use that. If you're doing a density calculation, you'd use it there. Electrical power dissipated by a resistor, you've got R squared, so you would use it there as well. Let's look at a calculated example. I measure a diameter of a wire to be 0.29 plus or minus 0.01 millimeters. Now, this is the diameter stated in meters, so that's 2.9 times 10 to the minus 4 plus or minus 1 times 10 to the minus 5 meters, just so I didn't have loads of points and zeros there. And with that, I'm calculating the cross-sectional area of the wire, which would be equal to pi times d squared over 4. Now, in this equation, pi and 4 are constants. There's no uncertainty there, so they won't increase the uncertainty of A. The only thing that's got uncertainty is D. So that's an example. Pi and 4 there, they're examples of this A in this general equation that I've used up here. And D is the X, and the 2 is the N. Okay, so what do we need to do here? We need to calculate A. A is pi times 2.9 times 10 to the minus 4 squared divided by 4. That gives me 6.605 times 10 to the minus 8 meters squared. So again, I'm keeping 4SF there. So I've calculated my cross-sectional area. I've done it in meters, that's why I use that value. The percentage uncertainty in D is the 0.01 divided by 0.29. Now, you could use these values if you were really eager, but there's no need to, because all I've done here is divide by 1,000, divide by 1,000. So if I do divide by 1,000, divide by 1,000, they cancel out. So that conversion factor cancels out. So you can just do a percentage uncertainty calculation using the values in millimeters. It's absolutely fine. And you get 3.448%. So I've got A and I've got the percentage uncertainty in D. Now I need to work out the percentage uncertainty in A. Well, the percentage uncertainty in A is equal to 2 times the percentage uncertainty in D, because D is squared, so I need to do 2 times the percentage uncertainty in D. That gives me 6.9%. And I've just finished up there in 2SF. And if I wanted to work out the absolute uncertainty, same procedure as we saw for rule 2, multiplied the percentage by the value for A, which was there 6.605 times 10 to the minus 8. Same procedure. So now we've seen all of the rules, and I hope that you've got a reasonable understanding of how they work. And I will do some, as I said, I'll do a video where I go through some exam questions, and hopefully that will further consolidate the concepts for you. This is just a little extra to say that Rule 3 is just an extension of Rule 2. This is not a new content that you would actually need to know. Okay, so for y, For this equation that I had before, y is ax to the power of m. Well, I could use rule 2 to solve that problem because the percentage, because x to the power of n just means x multiplied by x n times. So the percentage uncertainty in y would be the percentage uncertainty in x plus the percentage uncertainty in x n times. So therefore, the percentage uncertainty in y is n times the percentage uncertainty in x. We can actually use rule 2 to solve that previous problem we had. D is 0.29 plus or minus 0.01 millimetres. A is pi d squared over 4, which means it's pi times d over 4. A we already calculated, so I won't go through that again. And the percentage uncertainty in D was 3.448%. That hasn't changed either. So now the percentage uncertainty in A, because I've got D times D, rule 2 says if you have a multiplication, you add the percentage uncertainties. So I do percentage uncertainty in D plus the percentage uncertainty in D. That's 3.448 plus 3.448. That gives me 6.9%. So I get exactly the same solution. And there you go. Rule 3 is just a special case of rule 2. That is it for this. That's the calculations you'd need to do for experimental uncertainties. I hope that's been helpful. If it's not, then let me know in the comments and I'll see if I can fix up for you.